So I am Shankar. I am now faculty in Math and Stat Department in IIT Kanpur. I am the host, and the guest is Professor Tapol Prutomaiti. He is now professor in the Department of Stat and Probability in Michigan State University, US. So he will discuss about what is our plan, the schedule, everything he will discuss. We will try to follow the schedule, but sometimes we may change a little bit, but I will try to follow the schedule. Okay?
All right, good morning, everybody. Probably I should say good night because it's 8 o'clock. So if I'm sleepy, just say, hey, you are sleepy, so I should be awake again. Anyway, it's a pleasure to be here, all the across from the other side of the world. Before I start up the starting here, as Professor Dhar said, we kind of structured the whole thing in a kind of 4 days package. The first day I think will go a little lightly. Like first half mostly it would be introductory lecture, including I think I'll introduce you beyond the data. Typically I think in the course structure it's data science, big data, but how many you know about data science? Probably nobody, right, including myself. So we'll try to understand what we mean by the data science, and then when I'll go through some of these examples, we'll try to understand what exactly we mean by the big data and what the data science can do with the big data. Right from the beginning, let me make it clear that I don't know who you guys are. Eventually I'll ask you what is your background, which would help us. Nothing is fixed that we have to do A to Z in these 4 days. Rather than I'll be happy to do A to D as long as we understand A, B, C, D. So it's not our goal is to cover everything whatever we planned for. Rather than we'll try to follow as the way the whole it will flow the whole class. That means you will see that not just I'm speaking or Professor Dhar is speaking, we want you to be engaged in the whole class. And in the end of the day or on the workshop, definitely we have certain expectation, like you have certain expectations, which we can talk even today. So tentatively what as I said that I'll start with the introduction of the data science and then the some of the examples of which would help you to understand better about the topic what we'll be talking about. And as I said that don't think about that this is a pure statistics class, so nothing will start with just a formula, rather than it will start with a problem from a data science perspective, and we'll try to see what statistics can help us in solving the problem and which are the other part we need the help from the other disciplines. So that's the way we'll start. Nevertheless, as statistics is going to play the major role, so we have to understand statistics. So there will be some review of the things, starting with basic probability theory, which we'll do in the afternoon, and probably all of you know how to use R, but still I want at least you get familiar with what is called R. R is one of the very popular software. It used to be only for the statistics, but now for whoever call them data scientist, everybody use the R. So if you know R, that's fine. I can learn something from you guys. But if you do not know, at least do some basic thing with R so that when you go back, you know what R can do for you. All right, so that's kind of this day 1. Then we have the day 2, day 3, and day 4. But as I said, that all are tentative, so we'll display as the way we cover the things. All right. So let me start with introduction of the introduction. I'll come back with this lecture, and so here basically I'll just probably you guys know who am I, but still I'll introduce myself a little bit. Wherever I go, That's I typically spent about 10-15 minutes, particularly if I organize a workshop. It is sounds funny, although I'm from India originally, but I really never had organized a workshop like this, like spending 4 days in India. So this is possibly the first time I'll be speaking 4 days. So I'm very happy to be in IIT Kanpur to have that opportunity, 4 days. You might see that some of the slides actually created some of my students. Even I'll start like some connection. You'll see that more like some of the Chinese university I go pretty often, where I talk, so some of the reference would come from, but you'll get pretty good idea where I am from and what I'll be talking about in terms of what is my take in terms of the data science, okay? And so that your expectation would see that how the way I'm talking in the remaining part of these 4 days, all right? So as you know that I am from Michigan State, definitely today's perspective or this workshop perspective would be big data, data science, and the role of statistics in this business of data science and big data. So typically we are called the Spartans. Some of you probably heard about who are the Spartans. So this is essentially the Spartan, the football team. So most of the US universities are recognized, or the major US university is recognized by their football teams. So every team has a name, like we have the Spartan. Here is our logos. Either it goes by S, Michigan State, and this is our mascot. Okay, and we belong to this Big Ten. Here, although it's Big 10, that number again is funny because you can see that there are many more universities under this Big 10, but it started with Big 10 Club. So that includes Michigan State, University of Michigan, all these universities, all right? And so one commonality is that all of them are good in football, that American football, not really shocker. And all are major, like all the university has about 50,000, approximately 50,000 in that order, the student strength. So here is the Michigan State University. As I said that this, oops. This has not been changed yet. Sorry for that, because this is actually I'm referring from, I will take you from China to US. That's a, again, use of graphics nowadays, you know, we use graphics all the time. So here you go. So this is the state of Michigan, basically this part, and as well as we call the Upper Peninsula, and some of you might recognize these are the big lakes. So Michigan is fortunate actually to have all these big lakes as their neighbor or nearby adjacent. Essentially this is Lake Superior, Lake Michigan, Lake Huron, Lake Erie. So, and Michigan State is somewhere exactly right here. So that's we are from. You might see a little bit of this campus. It is a big campus. Just I see this IIT is also a very big campus, but I don't know in terms of the exact number. Like this is the football stadium. We are, as I said, that this is proud of. This is the Spartan. So all about this thing. All right. So you got to know enough about me. As I said that definitely I like to know about you, but that's later on. This is at the end. This is my office building. This tall building is my office building here. Of course, I have probably another space to share as well, but this is the main office building. Anyway, so you know where I'm from, right? Good. So anybody from among yourself is from statistics, or all of you are statistician?
Last two are they are statistics.
Okay, so this is good. Definitely, as I said, that to me, I born as a statistician, and personally, I think that this is the very good time for me to play the bigger role beyond that my office building. And as the way I will take you through, you'll see that it really opens up a number of big challenges to us. And either we have to be ready to take the challenges to work on this, that would probably bring much more discoveries, or we might stay away. So it would be the choice on us. But as you all already agreed that data science is completely new, so really nobody knows really what it is, but certainly there is a big discussion going on, and I will basically go through as the way I look the whole discipline, and as a part of building the whole discipline, like we have been developing the program in data science. So I'm very much involved in a number of these things. And that would actually help you to understand what is coming into the whole next 4 days. So that's the only reason why I'm going through this thing. So a little bit more about this buzzword data science, big data. Some of you know about Harvard Business Review. It is one of the most popular business review journal. They call this the data scientist is the sexiest job in the 21st century. So it's a high-ranking profession with the training of and curiosity to make discoveries in the world of big data. But note that once they say this, everybody actually is jumping in. It is no way it is saying that it is the mathematicians, statisticians, computer scientists, or anything. So essentially, whoever like to discover from this big data. And there is a big shortage of the data scientist, which is a serious concern, and that's the way. So I think in India also it is rapidly growing this job market, and they need some good data scientists, not really just a DA, TA, SI scientist, all these things. So here is a little bit more statistics again. Why it is so? Because there are a number of things already has been noticed, like McKinsey Global Institute, they kind of predicted that there would be 5 million jobs in the US, essentially just in US in 2018 with the skill of data scientist, and where the salary is above 100,000 salary, which actually can beat the PhD statisticians in the market, or any other engineers even from the market. So this is definitely money is one of the attractive point why I like to build my career towards that direction. And this was the #1 job in 2016. It is continuing. So what is a data science? If you look at the Wikipedia, this definition you might see, which I personally don't like that much, but Wikipedia, so I have to show you. But probably instead of reading this text, you might look at this diagram, which you can see that everything is there, like machine learning, data science, traditional research, which includes the math, stat, substantive expertise, all sorts of things. So traditional research is essentially some of the other science would come into the picture, who will give this data, which will talk. Math, statistics, knowledge, not really as a discipline, but all these things all together that might create the data science. That's kind of the Wikipedia definitions. So here is, from here on, it would be kind of my take that, as I said, that statistics is going to play a big role. Not going to, it is actually indeed playing a big role. And so which I typically I call the statistical foundation, which include the basic probability and statistical inference, regression methodology, and some of the statistical computation, including data visualization. So this part definitely is necessary part or kind of 1/4 or 1/3 of the data science picture. Just a side note that in these 4 days, mostly will be in these two, little bit here. Data visualization we might not do rigorously, but we'll do some. Okay, so this is the part will be covered. Then it has another big component is the computer science foundation, which would include database management, computing platforms, and some of the machine learning. But machine learning is, again, it's a common interface like we do as statisticians, we do the machine learning. Computer scientist also does the machine learning, but there is some commonality, there is some differences. Probably depending on how we are doing, I will touch base most of the statistical machine learning, but I'll try to contrast from the computer machine learning as well. This is a nice picture, right? That we started like this, and then with the computers, we are becoming the old age like this. We have to sit down all the time. I like this picture. And the third pillar would go as a information science foundation, which would be, now this term is little bit big data techniques, which include some of the analytic technique, which we'll be talking about today or in these 4 days. But to apply this technique, you need to handle or you need to use some specialized computational or the informational technique, which may not be doable just by my laptop or even your lab. So people are using Hadoop, Spark, all sorts of things. And it would depend on the size of the data as well as the complexity of the data. Oftentimes, size, we think directly that size could be an issue, but I might show you that certain cases size is not the issue, complexity is the much more issue. And then the data science, particularly the statistics, comes into the picture, how nicely you can counter that complexity so that you can avoid the other complexity like the computationals and data management, all those type of things. Okay, and last part is effective communications is important, and which certainly we statisticians are not good at that, and that's why we have to work with the other people who will do for us. All right, so these are the three kind of the main picture, and you can see already that it's not the statistics, it is actually everybody together. That's the way it is. So what is the role about of statistics in data science? So here, this one I like. You can read what it is. A data scientist is someone who is better at statistics than any software engineer, because you know that any software engineer or everybody does the statistics, but truly what kind of statistics they do, we don't know oftentimes. So a data scientist is someone who is better at statistics than any software engineer and better at software engineering than any statistician. So this part actually we are trying to introduce in our curriculum nowadays as well as much in parallel to the statistics training, that they need to learn really good computing skills, and then they can compete. Otherwise, anyway, as I said, that most of the people can understand the statistics a little bit. Of course, they have to know a lot more, and the statistics people has to learn a lot more of the computing, database management, all sorts of things, and that would be the data science. And that's why you will be get paid higher than statisticians or an engineer. Otherwise, you won't, right? So that's the kind of the idea to be the future data scientist, and statistics, how the way statisticians become a data scientist. Here is the, as you can see, for any discipline, what would be their disciplinary role in the data science, this is not very clear. But every professional group, like we belong to American Statistical Association, we also acknowledge that yes, data science is just not, statistics is just not the data science. But nevertheless, statistics is one of the main player of data science. And we are ready to work with all other people who are interested in to solve the problem, the data-driven problem. That's the much more common thing, that everybody is interested in data-driven problem. So statisticians can certainly be the part of that whole thing. Okay. So as I said, that this is not really a threat, rather than, in my opinion, it's an opportunity, and this opens up the door to talk with all other scientists. In fact, I think in last 5 years, probably I met a lot more non-statisticians than my previous, say, 20 years or so, how many non-statisticians I met. Because this whole thing, you are talking, and also I think I started solving different types of problem once I started talking with them, rather than what I wanted to do. So, so this is an opportunity to enrich every field of science. So, it's reciprocal. It is not like that we learned. Also, the other people like to solve a problem who they never thought about. For example, you might see that genetists, or in the genetic research, they have been using now heavy dose statistical modeling, computational tools. But even 10 years ago, they would not do that. They would probably use the simple basic probability theory. That's what they used to apply. But because of this opportunity, I think, or this data science things, this is an opportunity for the other scientists as well. So statistics, computer science, database management are the cores, but they are the core, but there might be more subdiscipline in the horizons. And as I said, this is much more open door type of thing. These are the three main pillars, but anybody can join. And in fact, there are many more players are in the field who are, but nevertheless, these three has to be there. That's the bottom line. So again, my take would go towards much more as a statisticians. Here is the enhanced role for the statisticians. We need to engage with computer scientists, database scientists, distributed computing, and course with researchers that generating the big data. So also, as you know, that to do the good statistics, you need to know how the way data comes in, or how the way data being generated. Sometimes you always, if I have a random sample, that means you can apply your probability theory. But when you go in this era, then oftentimes you don't know really how the way data is being generated. It may be random, may not be random, but still you need to know. So generation process is pretty important for us. It helps us to develop new tool, new thought that are compatible with the other researchers, develop new training program. So that's why this one of this workshop we have been doing, and there will be many more. So probably you have you guys notice this one as well, right? In statistics, you will see that lifelong we do the average. Essentially, we do the average. Even I'll try to argue when we will do the classifications, all these things, nothing but we do the average. But just average just doesn't work. Okay, so to even calculate the average, we have to be beyond average. So these are some of the things we have been doing. Promote reproducible research. We have been developing tools for others to use. That means today I'm here. Actually, I was hoping to have a lot more engineers so that I could learn more, and also we develop something which then you will be ready to buy, otherwise you won't. So far, because statistics existed over 100 years, but really did not penetrate that much as much we have been doing in last 10 years or so. Generally, we don't write the paper in Nature, Science, this type of high impact journals, because these are much more readable. Because always we think that the what we do so technical, it is not doable. But the big idea can be doable. So if we have the big idea, we should publish in this type of journal so that the others know that we can help you, or we can work with the engineers. That's the main target. And we have to train the researchers to work in teams. Like whenever you go to a company, then there is not really a statistician solving all problems. There are engineers, statisticians, other scientists all together, chemists, physicists, all together. So we have to learn how to work, not within the discipline, but between the disciplines as well. Again and again, this is big deficiency for us. Communications, and in fact, actually, this is the deficiency for all the researchers. In that way, business field is much better. They are much better in communicating. So they dominate. You can see that even in any company, the managers dominate, not really the medical doctors, not really the engineers, not really the statisticians. So here is the 5 things most data scientists to do, kind of. That's, again, this is not the exhaustive list or anything, but at least in this 4 days workshop, we should keep in mind, whenever I'll be talking anything, that we have something in mind always very clearly. What is our hypothesis? In other words, sometimes really what we are trying to solve from the data. We need to explore and visualize the data. As I said, that try to understand what the data is speaking about. Instead of assuming anything, let's read the data and see what it says. Then we need to build the models to understand the past behavior and predict future. That's kind of the things typically we do, because we learn from the data, try to understand the phenomena, try to understand the system, and then we develop for the future. Tell machine how to learn from the data, most of this, the machine learning part, and then tell the relevant business stories from the data. Not really everything would be behind, just the final part we need to communicate to our managers. That's it. So where we'll be, mostly will be 1, 2, 3 part of this 4. I don't think that we're going to do much on this last part. Okay? But nevertheless, these are the way. Again, you should not expect everything from me, because then I'm not talking really right with the data scientist. Already I said that we'll be doing some part, but trying to contribute towards the data scientist. Okay? So no way I would claim that we are doing everything whatever needed. Some of the softwares, as I said, that in these 4 days definitely you need to know R, but nevertheless all other things like SQL, Hadoop, etc. you should know. Python, most of the my students, they nowadays work with MATLAB or Python, but SAS, SPSS, etc. if you know, that's good, but truly for machine learning purposes this really does not help much. It is much more R, Python, MATLAB that helps a lot more. And once you know the whole thing, then you have to build. These things goes much more to sell the product. You have to package everything so that anybody can use, because your product would be used by the others. So that's what we need to know, some of these things as well. Data visualization tools, of course, you need to know, but we may not do much in this class. Okay. So we talked about data science and the role of statisticians. Now, what to do is with the big data. So again, then the question is, what is a big data? The general perception is that if it is a large, then this is a big data. Some people like to define that it is by these 3 V's: volume, variety, velocity. You can define whatever the way it is. And as I said, that oftentimes it is just not the size, but the complexity and the how to deal with. Like this traditional way, we cannot deal this part. So that might also be part of this big data. And That may be due to the complexity, that may be due to the size, all sorts of things, or that may be so quickly we have to do the conclusion that traditional way we cannot do this much. For example, online decisions we have to make, and show number of different way the big data came. Here is some of the thing. Probably you know or you don't know. More data has been created in the past because of this. This whole thing came with the information technology. In past 2 years than in the entire previous history of the human race. 90% of the all data was created in the past 2 years. Because probably right now how many gadgets I am using? Probably 5 gadgets I am using. 5 years ago probably I had just my laptop. And that's not even this first laptop, that was pretty old laptop. So even myself generating too much data. These guys are video, it's actually a data, right? Because so it's a huge amount of data they are generating. The total amount of data being captured and stored by the history doubled every 1.2 years, and 73% of organizations have already invested a plan or plan to invest in the big data. That's why every company is talking about, we have the data, you do something. But most often you might see that even nobody knows what to do with that. But we like to do that because we have the storage. If you bond, I don't know this is true or not because I got somewhere. If you bond all of the data created in just one day in the world onto DVDs, you could stack them on top of each other and reach the moon twice. At the moment, less than 0.5% of the all data are ever being analyzed and used. You can see that. So I'm not surprised that we are using less 0.5%. But now I'm going to argue actually we don't need to know more than 0.5% actually. And that's why the data scientist would be, because even these 4 days, probably you might see 4 hours are very important. All others are not wastage, but you need it. It's kind of ancillary. So anyway, so that's the kind of amount of data is coming. And here is this, I love this picture. It's everybody can understand, right? That you put a big ice cube in the water and you'll see exactly like this. And the big part goes to underneath the water, top part above the water. Using physics, you can actually try to predict that which part would go up and which part will be go down, right? So in a big data and statistics, how it goes where that we know we have this much of the data, but we just need to know this much. We just don't know where is this much, here, we just don't know. So that's the data scientist would be to do the big data. Nobody is going to buy this whole big data. It is essentially yours. I'll just try to capture some part. So now data science with the big data. So we talked about data science with the statistics. Now we have the data science with the big data. To make it short, essentially the relationship between data science and big data, everybody can understand. This is kind of there at the beginning. This is the data science. This is the big data. That I don't know anything. But if you look, just remember this previous picture. To handle this big guy, I need to know which part is your sensitive part. And I'll just handle that sensitive part, then you will become my friend. So, and how to do that? I have to be data scientist. So here, here you go. So basically, if you remember all these things, whatever I said, that forget about the large portion, try to understand which part you need to handle. Once you know this thing, then we are equal, even though its size is big, but all of us equal. Okay? So that's the kind of the role of the big data and data scientist. Already I said about the data scientist and the statistics. And here is the main sources of the big data. E-commerce, that's the biggest source in my opinion. Imaging, everywhere. In fact, we'll talk some of the imaging as well. These guys are doing imaging. So this is another big source of the data. Social media, medical records, that is another area. Satellite data, where most of the climate research, everybody is using the satellite data, and the government records. Day after day, every government using, so we call that e-government, right? So everybody is using this, recording all this data, so that's creating a big chunk of data. So all these resource, these are kind of the sources to generate the big data, and different sources create different types of problem. So we'll talk mostly about the imaging, and I don't think that we'll have, I'll have some example from the satellite data, but let's see. So the world is basically working on towards that direction. And as the way this is increasing amount of data, demand for data scientists will be definitely increasing. And the career in data science begins with the understanding of these three pillars we already talked about. So here you go. If you guys are ready, then we'll start the next part. So that's kind of my take about the perspective of data science. What do you guys think? What is your expectation? You like to be data scientist, all of you, right? Okay, so anyway, so okay, I think that's the there, but you let me just make sure you all understand that these three parts you should not see as an independent way, because these three existed long time in our society, but we never worked so coherently each other until the data science comes in. Okay, so I will believe that you might have expertise in one of these things, and in these 4 days we'll try to learn much more how the way statistics make the bridge among all these things, or why we need the bridge. Sometimes definitely within these 4 days I won't be able to make the bridge here and here, but at least we'll try to understand why we need a bridge. Okay, but in some cases I'll try to show you that how the way we have been working on that. All right, so that's kind of the introduction of the introduction. You already, I told you who am I more in details, and you will see that in 4 days probably we'll talk even more. As I said that I really don't like that completely one way communications. It will be much more to both ways, so that the whole, it would be much more enjoyable. You might have something in plan, but what our expectation is that right from the beginning you digging into one piece of thing. I'll probably, even by the end of the day, I'll say what do I mean by one of the thing, but it's preferable, given your discipline, you try to understand that this is the problem I like to solve, and you do whatever the way you like to. So what we are trying to say about, I'm not trying to tell you that you do this type of statistics. I'll just pose number of problems, and you can immediately start thinking about your solution. Because given a data, the computer scientist is going to work one way, the statisticians are going to work in some way, and the scientist who generated the data, for example the genetist, he has some idea that what to do with that thing. You do all these things, but all of us are trying to reach not the same solution, but same question of the same answer of the same question. And in the end of that day, we'll see where we differ and where the deficiency is, why all of us need to work together. All right, so that should be the expectation, that right from the beginning you start thinking about solving a problem, and we'll discuss some of the problems where I'm much more familiar with, But I'll be open to discuss any problem with you guys and see whether we can exchange any ideas or not. And kind of the remote way I talked to Professor Dhar that if we could build a group, working group eventually, where probably non-statistics part would be much more from you guys and we can help you with the statistics part, that would be nice. So, no matter by the end of the fourth day, you need to present something in front of me that you learned this part or you like to do this thing. You might say that I don't like this thing, that's fine. I'm willing to take this thing, that I don't like your statistics. You tell me, I'm fine. And let's see, but we are targeting the same question. So for example, I'm trying to identify a gene which helps me to talk through our, say, 4 hours at a stretch. And you try to find out, I try to find out. And if we differ, let's see why we differ and if we can resolve anything. Okay? Because idea is to solve some problem. Idea is not to teach you just the statistics, but what the statistics will do, but how some of the techniques to apply, you need to know some of the statistics. That part we'll try to cover. Okay? But we are not going to examine you on that statistics part, rather than we'll try to examine you how the way your perspective is to solve a problem. All right? Any question? You can see that it's getting midnight for me. But no excuse. Okay, I'll continue. But sometimes some comment would be good from anybody. Okay, so what is next? Next is we'll go through, basically walk through some of these general questions and see what is our perspective towards that general questions. Okay. Again, you don't need to think from the statistics perspective. You don't need to think from the computer perspective. You just think from the data perspective. That if I have the data, how to solve this thing. If I don't have the data, what data I need? Because any data may not solve any problem. So then what's the data I need to solve this problem? So what is the commonality among us would be how to look at the or look at the data perspective, how to solve the problem. Okay, you are pretty much one good time because this is our kind of the next page I am. Let me start again, very ordinary example. Again, few things I have to make sure. The way it is kind of still look like a textbook type because I am kind of extracting some of these keywords, putting it here to think about a problem. But in general way, it won't be like that. You have to actually formulate the problem. You have to write down in your language. You have to really be precise so that you can solve the problem. So some way, so what does it mean? Remember that I had that 5 points for the data scientist. Number 1 is the creating the hypothesis. So in these 5 examples, sometimes I will give you the hypothesis, sometimes I won't give you the hypothesis. That means you have to think about, right? Here probably the hypothesis is given. So a hospital surgical unit was interested in predicting the survival periods of patients undergoing a particular type of liver operation. How a data scientist can help to the management in decision making. You know that the final decision comes usually again from the manager, not from the doctor. Doctor will recommend to the manager, based on certain thing, based on his science, but the manager will make a call, right? So again, from the data's perspective, how many of you believe that the whole medical science is actually based on data? It is actually on data, but subjective, very, very subjective analysis on the data. But what we are trying to do, I hope in 10 years, data science can help them a lot more to take that subjective decision a lot more science perspective, but science of the data perspective. So that because we are getting the data and now we are learning how to analyze the data, and they can do those things and then make a call. Like high pressure, they have a chart from here to here, low pressure, from here to here, high pressure, but it's all data driven. But now if you have much more data, you can actually have a better things to do. So how the way we can do it here? We can start thinking very simple way. Definitely we need some data, right? What kind of data we need? So we need a data. What kind of data we need? Simple way, if we think about, again, starting very simplistic, statistical thinking goes on. But next one I will see that I'm not going to throw you so much statistics. Survival time along the clinical, along with clinical and vital informations, that would help you, right? Like you did this, you collected number of patients, but say for example you have to identify some of the hospitals where this particular surgery goes. For example, prostate cancer surgery. So then what you have to do? You have to go basically some of the hospitals who does this prostate cancer surgery, look at the survival, follow-up period, and usually hospital has some of the records like their age, like maybe their race, some of these things, and you might try to develop a model. But before saying the model, what you really like to do, how the way you could answer, because doctors actually don't do any modeling or anything. How they do? Simple answer. They just look at how many days the patient or how many years the patient live after the surgery, right? But what they are doing, simple mean, nothing but they are doing calculating the simple mean. Then why do I need a model?
To generalize,
to bring more confidence.
Okay, that's a good point. So why I'm trying to say here, I'll try to argue that, see, if you the mean, anybody can calculate the mean. Although statisticians can claim that we own the mean, but nobody own the mean. Anybody can calculate the mean, right? So in that way, it is actually everybody's domain. But we develop a model. So basically, I don't know whether I'll get a time today or not. We'll see that this model, let's not use the word generalize, but I'll try to show you how the way a model can make the answer much more precise. Still, it will calculate the mean, but much more precisely. So, for example, if you use the regression also estimate the mean, but it does much more precisely. So if I have the data, then I have to actually know how to develop a model which would make my answer much more precise. So we need to understand some of the model developed. We'll start with, as I said, the simple model, and then we'll go with a difficult model, but I don't know whether we'll go to a different model or not. But let me just continue with this thing. Say for example, I'm just putting together that along with some of this basic data, like we talked about their age and maybe the racial group, but some way their gene expression has been also collected. Some of you know that this is also a fairly modern technology. We can collect the gene expressions, but it's still fairly expensive. But the technology is very well developed, And gene expression is kind of your very individualized information. Age is actually not that individualized information, because for the same age there could be many more patients, or age 60 versus 61 there is no difference, or age 58 to 62 given that prostate cancer operation there is no difference in terms of the risk calculation, but in terms of the gene or gene expression it could be unique, right? So if I get that gene expression, which means that I can do the individualized prediction. Still I'll be doing kind of the mean, but the very, very much individual level. So given a new patient comes in, but how do I do that? How many of you have seen gene expression data?
That I precisely want to know what type of data that is gene expression.
So here is the good thing. That's why we precisely know. That's why we need to sit down in the biotech class even. So when I started learning this thing in 90s even, actually I went to some of the biological lab, but most of the biological lab actually does not create, because it was owned by most of the companies, big pharmaceutical companies. So there is a very brief discussion, short write-up. Long story short, it's a technology. It's a lot more engineering than just the biology. Long story short would be, it's like a cheap rectangular to 1.2 inch, 1.5 inches by 1 inches type of chip. Then you take your blood, put that here, and then they put a laser and different types of intensity of the light you have to measure. Again, everything is a machine driven. So accuracy, all these things could matter. And how the way this intensity measures, that kind of transform into the data. And typically this chip would look like, here is one of the way, it is different intensity. Basically this again, first thing it's come in image, then image transform into a numerical value. And say this is kind of the one individual, it has number of genes. As the way the light densities are, it's kind of identifying what is the expression level given that particular phenomena they are observing. Okay. So I'm 100% sure I could not answer you all these things, because we have to spend 4 days on that. But it is well developed technology. Now the technology actually moves up, so which generates a lot more data. But let me tell you about what it is in terms of the data. So what it gets, if you have one individual, then immediately it generates almost 20,000 data points. Like your 20,000, about your 20,000 gene, here's the different name of the gene, about your 20,000 genes, how they behave if you have a cancer, we can see these things. Similarly,
those observations are three-dimensional. That means
no, this is not a three-dimensional observation. This is just one. When you finally get this observation, some number you will get here. Some numerical value you will get. And that numerical value would depend on the intensity of the light when they put that slides on the laser, then they measure that intensity of the light. So it is.
This is your data.
So this is essentially look like data.
The numerical values are the
Numerical, all are derived. It's not like what is your income. So this is a very good discussion, because it's kind of, you can see that immediately when we have other data, it's not really the same way it is coming. All other type of complexities are also there. There are some processing error could be there. What you get, that exactly what it mimics, all sorts of things are there. But let me try to, whether you can get that whole complexity or not. So first thing I just said, so these are the patient group. There are about say 8 or 15 individuals, and there are non-patient group about 15 individuals. They like to see the differences in terms of the gene. Like 15 say prostate cancer group. It is not exactly prostate cancer, but it is something. But essentially you can think about a disease group. This is a non-disease group. Only 15%, because as I said, it's very expensive. Even when I worked with the corn data, disease corn, non-disease corn, we had only 3 samples because it was that time very expensive. Right now it is cheaper. But so individually you can think about one of the data point. That's what you need. Like if you develop a model, individual 1, how long that patient survived after the surgery. Patient 2, how long survived after the surgery. That's the way you are getting. So you have 15 patients, how long they survived. But then you wanted to have more data. You said that if you have more data, then your answer could be more precise. What do I mean by that? That means for any given individual, you have that age, and then you have about 20,000 more data. Okay?
That means 20,000 genes.
20,000 gene, but 20,000 characteristics you are getting. So initial data was our simple statistics when we teach in the general just simple regression class. I have one individual, his age, individual 2, his age, individual 3, his age, and of course you are writing as an outcome how many days survived. So you'll have probably say total 15 patients, 15 age. You can run so you have 2 parameter regression model, you can run all these things. But you wanted to have more data. With the technology I gave you more data, and for each individual you have 15,000 or 20,000 more variables, right? But I'm not giving you too many more patients, because patients are, whoever is coming, I'm just getting this does not cost me in terms of getting a new patient. Patient is already there, I just collect their gene expression data. So what it creates the problem? You wanted to have more data, I gave you the more data. Now your duty to give me much more precise answer, because we all agreed that if I had the more information, I could have a much more precise mean calculation or personalized prediction type of thing, right? What the complication comes in. I have 15 individuals, total 30 individuals. 20,000 parameters I am injecting. Now can your simple statistics class, whatever you have learned, can you solve it? Or whatever the way you will like to do it. As I said that, forget about the statistics. I don't like to talk much about the statistics at this point. I gave you the data. You wanted to have more data. I gave you the more data. You find a solution.
That means your sample size n equal to 15 and p equal to number of parameters is 20.
That's we formulate. That's again, since I have been talking in this way with my experience, it's kind of a formulated way. But you could formulate differently. Somebody else could have formulated differently. So how would you do that? You can do it. So you have one formulation, which is typically that's the way this problem, at the current stage of this problem is right now, we have been solving. But there are many different ways. Previously, as I said, in the 90s, your number of parameter more, number of sample size less, solution was not there. But still this problem we solved. We did simple t-test. What we did, everybody understand t-test, right? Because you just t-test, see the difference in the mean. If you have 2 groups, I have a disease group, I have a non-disease group. Then what we have done? For the disease group, for each gene, I take a mean. For each gene, I take a mean for the non-disease group and just see whether there is a difference or not. Then I went to the next gene. I checked whether the mean differences or not. I went to the next gene, mean differences or not. That's the way, kind of the solution. Okay? And that has been published in PNS or like proceeding of National Academy of Sciences. That was the beginning. Now we can say, oh, this is wrong. I'm pretty sure Subra would immediately say, this is wrong. What you guys have done? Yes, I have done wrong. But what was, I had the solution. So what is wrong? But in any case, we can always, for a given, any data-driven solution, we can always argue from different angle. Like from the statistical angle, we might say this is wrong because, but again, at the same time, we do not have a right solution. Most of the cases, we do not have a right solution. The solution you can have in the pen and pencil, but that cannot go to the in practice. On the other hand, this gives a big benefit in terms of the calculation. I had to calculate just mean based on these 15 observations instead of 20,000 observations. Go back to even say, as I said, that 30 years ago, 1990, 1985, there are a number of things. Not only the data you have to calculate all 20,000 together, but before that you have to process all these things. So this thing also can be like something called the normalization of the data. All sorts of things comes into the picture. Okay, so the computational aspect was also big. As a result, breaking the problem piece by piece was kind of an innovative solution at that time. What was innovative in 90s, possibly it may not be innovative right now. But the whole point is that this solution actually, I have to acknowledge that actually we the statisticians did not provide this even simple solution. We only criticized. But this actually the solution came from the scientist who had the data, and they asked us. We always think about, oh, this is the way, if I do it is wrong. We have been keep thinking, but they actually tried to solve the problem. They tried to understand where the difference would be, at which gene would be the differences. So if they can track that particular gene, then the next patient comes in, they might see that particular situation of that gene and try to understand what should be the survival of that new patient would be. That technology is still not there, but this is coming. In the personalized medicine, this should be coming. So that's why we have been talking about gene therapy, all sorts of things. Why we are talking gene therapy? Because we are able to understand the differences in the gene, even with this small data set. So here, now so number of good things coming. Would you call this is a small data or big data? Sample size is 15 and 15 total is 30. In terms of the mean test, as I said that you can do, that's the way we have done. Now we have the technology to do even all together, but this is a small data or big data. And not only 20,000, actually you can have even many more. With the advanced technology, with the advanced biotech, you can have many more. Very cheap. Now it's very cheap. Not only that, the patient is going to the hospital repeatedly, right? Because the day he went to the hospital and surgery was done, it's not like that. Probably he has been observed over a period of 2 years, over a period of 5 years. So actually I can have same patient number of gene expression as well and see if there is any dynamics or not.
Does it change along the time?
Some of they're observing, mostly it is in the plant yet, that it might change depending on the photosynthesis light, how the way it comes, that might change. So what it's basically a kind of the longitudinal study of the or the dynamicity of the gene expressions. So oftentimes change may not be significant, but nevertheless, since you are able to capture all these things, you take the data. So what is the problem becoming? As I said, it's a very good point. The problem is that you just take the data and then it would bunk on us, but we don't know once you have the big data whether we should use or we should not use. The first thing we have to decide whether we should use or not. So for also just go to the one-dimensional way. If I can identify only few of them are important, all of them are not important. So one way I can just take only few of them and go for the future model building. I don't really need to do all sorts of things. And that's kind of the data science is doing. Still statisticians will hesitate to do that way because we'll be talking about total uncertainty measurement, all sorts of things. So, but nevertheless, that's possibly the current status of the data science, that you take the problem piece by piece and try to come up with a solution. Okay, so this gives you from a simple problem to you wanted to have the data. Once you get the data, you make your life much more complicated. But it would be good if you can answer very nicely, it's really horrible, even with this additional amount of data. If your answer does not make sense, then it is horrible. That means you did not. So it's better not to use the data then.
Is this data publicly available?
Yeah, yes. This data is publicly available. In this one, like gene expressions, as I said, that it's kind of the dated. Right now, it's much more coming imaging data, genetic imaging. That's what. But along the line, you can use this one as well. So there are tons of data are there. What is not publicly, so all still are experimental. But once the whole technology would develop, I'm pretty sure that all hospitals, when you will go, they will do your gene expression things and show that your personalized medicine, they can prepare your personalized medicine. But the whole technology is not there yet. It is still in the lab. So what we have to do, people like you guys have to jump in and develop the whole system so that people can use, common people can use, because doctors are not going to understand a single thing about all these things. But so far problem is that few of us really work with the doctor as well. Shall I make this even more complicated? Probably I will. But before I move through, did you understand the essence of this example I'm talking about? So any data set you can download. I'll show you some of these things. You can start working right from the beginning. You don't need to think about whether I'll criticize your statistics or not. Okay? You think about solving the problem. So as I said, I try to see what is your thought says how to solve this problem, because I already acknowledge whatever the way I do as a statistician, you may not buy it even. But that is our satisfaction. So there are many questions to solve. Which genes are different? Do the genes have any predictive power? Because difference may or may not have the predictive power. Those things we can discuss. But anyway, this generates number of things. Another error. So this is related to, you can think about text mining, data mining, whatever the way. Nowadays people are using the machines all the time. So what it is, particularly the identifying the number, you can see that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 things. This related to a special problem, but it can come in any problem. This is a very classic problem, has been analyzed in this book, Element of Statistical Learning. So what was the problem was, in US, you know that when the postal service deliver your letter, it has 4-digit like pin code. We have the zip code. We call the zip code. It's a 5-digit zip code. Like my zip code is 48823. So, and US is one of the most automotive country, right? So when it comes all the bulk of this all mails, it has to be sorted out, and typically sorted out by the zip code. So machine has to sort. So what does machine does? Machine try to understand what the zip code would be. That means trying to understand whether it is 0 or whether it is 1 or whether it is 2 or whether it is 3, all these things. And it will sort out how the way it can be solved. How it is related to the data science.
Image recognition.
Say again.
Image recognition or that.
But what is to do with statistics?
So first, like from image to get the data in an analytical form, and then find that what the pixel-like kind of the pixel, what pixel is influencing to which character, some kind of machine learning models around this.
Okay, so you got the sense, but why it is a data science problem? You take the picture, machine will take the picture, like he's taking my picture, or if I open my phone, it will take my picture, open the phone, right? But I can show you probably, it may not open sometimes. So what does it mean? That means when it takes this picture, in the background, you are doing some data analysis. So typically what it is, some way, essentially you read the depending on the resolution, you read the data in a matrix form. Like for example, this one probably 64 by 64 matrix. Nowadays there are many more 256 by 256. And then you kind of use, there are many different way the restructure whole thing and then predict whether it would be. So if I get some time, probably I'll go some of the behind the story, how the way, like we can use even Fourier series to transform back. Like you take some of these significant coefficients, very quickly you have to transform back. Because depending on the resolution, even what's a good nowadays good example is like taking the photo and then reproducing my photos, right, immediately. And if is very high resolutions, it takes a lot of time. But I'm moving all the time, right? So it has to do very fast. What does it mean? It has to edit. If it is a 64 by 64 bit, actually you need to know probably 16 pixel very well. If I can identify that 16 pixel, I can reproduce the whole much better way. I don't need to know actually 64 by 64. So in other words, what it is doing, I am trying to identify some of the characteristics, but there could be a mistake because what we are trying to do, it is again it will be probabilistic match. Some probabilistic sense it will be matched. So probably I'll do some part of this part. So that means there is no guarantee that it will produce the right thing. So I have to build a machine which would give me the highest accuracy, and in that case I should be able to use my machine so that there would be less misshot, everything would be correctly sorted, and it would be much more reliable. But behind the scene, when you do this thing, when you are handling this huge volume of this part, you cannot really apply this traditional image processing technique, because then it's not worth it. The two things, it's a time, and second thing, it also cost for other infrastructure cost. So you have to do very fast. So now we have this technique which we are trying to prove that it can be as accurate as you would have done with a whole 64 by 64 bit analysis. But I have to prove this statistically that this could be. So both, I think this type of problem at this point we can do, even theoretically we can give some proof that it can be this much accurate, like with mathematical bound, and it can reproduce in some cases it is not. So these are the problem very well solved. Which problem is not very well solved? Still, I think the phase is not very well solved. But people are working. That's why the deep learning and everything is coming. But unless we try to understand what the data science behind, it would be very difficult to say that this is working very accurately. Why? Again, think about that thing. We are trying to extract only more small portion of the data from the whole big picture and try to reproduce the whole picture. That's why there is a more likelihood that I will make a mistake. But I have that my statistical test procedure has to such a powerful that I should be able to detect only the important characteristics. All other characteristics I have to just remove. That's the way the machine can be fast. But then what's the probabilistic guarantee that I can provide? So that's the statistical machine learning theoretical research going on. It is moving very fast, in fact. Okay, so let's move on. So this is, you guys since talked a little earlier, 16 by 16 pixel already you know, but as I said that I might talk later on much more. But more important, coming back to the same problem. So this prostate cancer, so you wanted to have more data, I provide you with the more data. For the time being, think about this is not a prostate cancer, it was a stroke. People has the stroke, right? So whether you have a stroke or not. That also might depend on the gene, because some people get hyper very quickly, some people are very cool. That depends on the gene expression. So you have the gene expression. So I give you the gene expression. Before that, again, doctors will say, oh, well, they look at the family history type of things, but that's small amount of data, again, subjective. Quantitative analysis, very subjective way they do, right? And then we did the now we got the gene expression. You said that you'll get some improvement. What else if I provide so that you can be even much more accurate? What the other things might matter? So nowadays, also the other thing coming is the brain image. So there are a number of technique. Again, it's pretty well developed technique. Some of you heard about EEG, right? One of the particular data set one can see in this archive. So what it is, how many of you have seen this picture or have seen in the, so to take this, what happening in your brain, basically they put some kind of the electromagnet, like 64 of them, or it depends how many, depending on your head, depending on the infrastructure of the hospital, all sorts of things. And then you try to look at how the way neural level changes going on through that particular channel area in these things, okay? So which means that what is the thing is that I'm giving you wanted to have more data. When the patient in the hospital, I took his already the gene expression. Now I'm taking his brain image as well. So I give you the brain image. Does it help you? Answer is yes, you would say, but help me. You do something, do the data analysis again, calculate the mean, show me your mean estimate is better, or the prediction survival time is better. How do you do that? So to understand something, so how the way this data would look like, first thing, it will create in a summary way as many channels you are using, that many channel you can think about, although there would be a little bit more details which I would go. So at this point, each channel will produce, because it stays over 2 minutes of period of time, it will produce a time series type of thing. And typically this would look like, these are different channel, that this is the way the whole data, you can transform it to a numeric number, whatever the way numeric number, but again here would be we can talk or we can spend few more minutes. So but in any case, you might see this type of picture, and how many plots you will see, as many channels you are putting.
But what is 0 to 500?
So GS time point. It's scale, but note that actually it is a continuous thing. It is continuously being observed. So, but let me first, so if I give you this data, what is your idea? How the way you can, in conjunction to the previous or just this data, how the way you will use it? You don't need to know statistics again. This is also a data.
This is a data of an individual.
Data and individuals, because like in a gene expression case, you get 20,000 gene expression. Here you get, I think this has 64 channels,
Okay.
and this is the type of the like 500 seconds you observed. Think about it of an individual. So what are the complexities brings in? We all were looking for the data, right? We said that we like to have the more data. Now I gave you the data. First problem is that how do I get the data? Because so first thing, how do I get the data? In one way I can think about, I'll just take the average of a whole thing. And then I'll get, if there are 64 channels, then I'll get 64 additional data points from his head.
By average of these means?
I just said over these 500 time points, I observe this 500. I just component wise take. Somehow you have to think about how to use the data. So what I'm saying that whatever you say, there is some problem.
No, average means you will be getting another curve.
No, I'm still not getting the curve yet.
Okay, Okay. For each card.
Each card.
Okay. 64 numbers.
So let me tell you one thing. When I talked to a particular doctor, actually the radiologist was doing this thing. What he did, because they're the person who are generating the data. We saw after they published some paper, right? At the very beginning, since it's the data, you can just think about combined whole thing, just create a number. It identifies something. What you like to know? You like to know some more about this individual. So even if I combined all this information, just take some average, all this channel, it gives you something measurement of your head, related to head, which represents something. Because all this data, if I average for mine and if I average yours, would be different. So that means I get two different numbers. And they just use that different number and see the differences or not. So what they did actually, just the mean test, is the difference or not. But that's okay. That's okay because that's the way first, because they are not the statisticians. And still you can see that we have the doubt right now. If like three of us, I know that we are the statisticians, we'll all differ how the way we'll use the data. First thing, now, if it is a 64, this 64 essentially also depends where actually the radiologist putting this channel in the head. Typically there is a registration system of our head, and each is the coordinate wise, like XYZ type of things, and you can put that channel exactly on that thing. So you know what is the difference between these two curves, like physical differences between these two curves. But say again, since it is from the same individual, all this may not have complete independent information, right? In this, all this practicality you can think about, all the science inside of the data you can think about. Then you can think about.
To clarify, if I put the channel in a different place, then you will have different card.
You might have. So you can think about it as a spatiotemporal model, or another, if you have the more capacity about this whole thing, this actually is an image. When you plot this thing, you took that 100 second, 200 second, 300 second to plot this part, but actually it's an image, whole thing. Your kind of this particular, they measure some kind of the change in blood pressure, a very indirect measurement it comes in. So it's a whole image how the weight is changing, okay? So if it is an image, then really you don't have this on piece of data. So what essentially you learn, that's something called the functional data. So one can look at essentially each of the function. So sometimes the function, we treat that as a time series, but time series and function are fairly different. It's not necessarily the same. Oftentimes we might use the time series type of technique to approximate the function, because as I said, there is no separate, we just observe, this number is just artificial number. But otherwise it's a continuous change, how the way, like you see me, how the way I'm moving. Each second is completely different. You are just thinking that from here to here probably the same, but each second is completely different, okay? So which means that if I really look at the data in that scientific sense, it's almost impossible to capture everything, okay? Then the question is, how much portion I'll capture, how do I capture? And then, of course, you wanted to do the model, you do the model after that. So you are increasing the data size as well.
I didn't get, why did you say that these are the artificial one? I didn't get that.
So,
Does it not represent time? That's what.
it's over the time. You are just measuring that thing. Like in this point, you are measuring these things, but actually it is continuously changing in between as well. So,
But that's what will happen in time series model.
but you don't really bother about it. Every year GDP is how much. In between change, there might be some physical, but essentially you don't capture that part, and probably you don't need to, because you are interested in every year end. Some of the things like for your salary, that's a time series because each year your salary changes, but that's not really functional because in between really there is no change, although it's a time series. Let me just make it clear. On the other hand, my blood pressure I am observing over 50-second period. And over the 50-second period, I observe in 10 seconds, I observe in 20 seconds, I observe in 30 seconds. But it is changing continuously. If I could have observed in any millisecond, truly I should have seen completely different thing. But it's not doable. That's what I am observing in some points, right? So that's why oftentimes we call these things are infinite dimensional problem. Truly, whatever making out the dimension is artificial breakup. We are breaking up. We are putting. Of course, we are making some assumptions within this small interval. There is no change. All these things, but the whole physical process changing, actually.
That's a limitation of the data, basically.
That's the different types of data. That's so in the past we never used to use this type of data into our statistical models or in the model building process, or even if we use it, as I said, we just treated it as a traditional data piece, like we take the summary, we take the discrete data and put it into other model. That's the way we have done, because we did not have the mechanism even. Just the used term I have used immediately, if I say it's an infinite dimensional data, really there is no way you can use the infinite dimensional data. It only exists in mathematics. But now what we are trying to do, we are trying to develop, or we are trying to essentially practicalizing that concept of the infinite dimensional thing, how to use into the practical way. So some of the things probably we should be able to cover in 4 days. Some techniques, how to capture this part. But my point is that this is one way we are thinking. You can think any other way.
But I could not understand the earlier picture, that 8 diagram, the first row and second row. What does this picture means? The picture with those cards, this brain picture. That means there are 2 rows.
No, so you should not think about this one is exactly as many things are there. This is a changing kind of dynamic change of your one part of. So I'll show you maybe. So typically how the way the brain get registered, I know a lot more about the fMRI, which I'm coming in a minute. Your brain is usually chopped into number of pieces, like 72 pieces, like this way. And then like this way, 80 pieces, okay? So when we see this thing open up, so basically one of the cross section of this brain is here. And this cross section picture, whatever we capture through this channel, that's the cross section here. This is a cross sectional picture, okay? So you should not think about these are the channels. This is one of the cross section, how it changes over the time. And this is one way of looking. And then what the time series plot, that's the when we just look at one of the data extracted. But truly, this is the image. So doctors can see that image as well. But for our analysis purpose, this image, how do I do that? There is no data. Actually, that cannot be put as a data. We have to change it either in time series or something, and then we put it into our formula. Okay, so the bottom line, whenever we are thinking about the image, all these things are data, then it's making our life really, really measurable. But at the same time, we love to know all this part. But whatever we do, some kind of ad hocness is there. So in a broader way, then what we are trying to think about, this is probably the last day even Subra might talk about. Not this one. Let me so move through. This is EEG again. I think getting.
I do not know anything about big data.
No, you don't need to. I'm going to say what exactly we are going to say. As I said, these techniques are not all developed. So here is another way. You heard about functional MRI? Anybody had functional MRI? How many seconds did you go through this scanner?
15 minutes.
Every 50, okay, it might be 15 minutes. Okay, typically what would happen? By the way, I have been in the scanner. One of my students also have been in scanner. And he saved his data to understand. And then, because still he's developing some of the statistics. Like you, he don't know the big data, but he saved into a DVD. And I gave my data as well. Once his model is developed completely, he can do this analysis. Because in our university, we have that lab. In fact, one of the radiology I work with, he did the whole thing. Because data extraction is much more difficult. But whole thing actually is physics. Like when you put this one, as I said, that under the scanner registration system is three-dimensional. You go like about 72 pieces, about 80 pieces. You make this cubicle, and then every 2 seconds or 2 seconds, 4 seconds, depending on what kind of testing you are doing, you take the image. So what does it mean? That means it create. So if you have this three-dimensional, it's very approximately 70 times 70 voxels, we call the cubicle. Typically, these are all individual neurons. Actually, so the whole registration system, that means this radiologist, when they developed, it try to capture your all neural level changes, what's happening over the 2 minutes time period. So that means your brain actually generate, or the data source is this many. Anybody can calculate immediately? You can see that huge, right? And then what it goes, every 2 seconds, it's clicking. Every 2 seconds it's clicking, or 2, 4, 2, depending on the design. So basically, it might happen that, say, 120 time point you are capturing. So from a single brain, you might capture this many data point. Okay? Probably it's very close to more than 500,000 if you calculate this part. So your gene expression was 20,000. Immediately we had so much argument. Now with that 15 patients, I gave you this much volume of the data. About 500,000 just I add it up. And you said that if I get the brain data, I should be able to predict this guy whether he will have a stroke or not, right? Do it now. I can give you my data even. You do it.
Can you explain 17 to 17 to 17?
So this is very your cubicle way like this. How many cube you will get in your head? X, Y, Z type of things. Okay. Of course, this number would depend on which machine you are using, which scanner you are using.
Does not depend on the size of your head.
Actually, everybody's head would be. It's like it has to be registered accurately. So everybody's head has to be registered in the same system. Otherwise, we cannot really compare one head to the another head. So there in international standard, there is a same XYZ coordinate is well defined. So even if you're short, like your brain is actually bigger. So you might capture all this part well. But typically what we see, if it's a small brain, quite a big part is kind of the gray part. So you kind of discard these things. So some people may not have any data for these things, but some people might have the data in everywhere. And nevertheless, even in the brain, if I have this thing, I'll show you the whole picture of this thing. Most of your brain actually has no data. Your neurons are actually very small regions. So most of the data actually you can delete by looking just from the machine.
But then why they take it?
Because it is coming in the scanner, we cannot just erase this part. We have to erase as a post-processing of the data. Not really right at the beginning I cannot determine these things. So all you know that brain initiative, brain is like BRAIN, brain research, A for I is the initiative network. So there are number of countries including US, China, France, Germany, spending billions of dollars here. Billions of dollars. So right now what I have the data, 187 Chinese Beijing lab data who are studying this fMRI things to understand the brain thing. But my students are having real difficulty. They cannot really keep the even single patient's data in their laptop. Forget about running the model or everything. But so coming back to the point, so think about, this is basically an array of this thing, and this each array, so in a two-dimensional picture it would look like this, and each one will have a time series like the way we showed if we take these things. But since it is the same brain, as some of you already said that this may be related, so some way it might create some kind of network. We don't know. So what the other way you can think about, so number of things, imaginary thing goes on. Either I can think about it's a three-dimensional matrix, the data, that each matrix entry is a time series. I can use that data. Or since they are from the same patient, actually they are really network. So the data is essentially the network. Then you are observing number of network because the time points changes. So it's a moving network or dynamic network.
Network is single, but network is moving.
Network is moving.
Network is moving.
Yes, just network itself is moving. So, but we don't know. That is again when you said that network is moving, really how the weight is moving, whether network is changing, how the weight is changing, nodes changing, age changing, when it's changing, we don't know anything. But what I'm trying to say, capturing this type of data, it is just not, so first thing, how huge you can imagine, this is just for one individual, and then the complexity, how the way you like to capture. If I put it to this matrix, still in the storage way, I can X, Y, Z coordinate I can use to storage. But if I think about it is a network, then how do you store that network data? Forget about statistics, right? You have to store this thing. How do you do that? So first you will learn, you can go to the, I can give you some website, you can go to the website, download a data, it will see essentially this type of image, try to extract the data itself. There are a number of software, by the way, available, and statisticians has no contribution over there. But all these things, statisticians need to understand the whole processing part, how the way, as you said, like I can think about a time series, I can think about a continuous thing, how the way you are thinking when the data you extracted. Okay. So you can understand that you have to solve this problem by the end of the fourth day, right? Because I'm not, as I said, that I'm not going to look at your statistics. I'm going to look at how the way you're solving this thing. And if I provide some solution, then you have to buy it. Buy it means that you have to sell it into your own discipline. But I'm not saying that this is the solution. I said that I could do something. If you can do something, do it. Okay, that's the data science should be. All right, how does it sound so far? Okay, so we'll see. But at some point of time, I already mentioned that at least one piece or two piece that you can think about the functional piece. So then you need to know a little bit about how to deal with functional data. So although Subro said that he doesn't know any big data, I don't know any big data either. You can see that. But the technique, functional data analysis, would be useful. So I'll introduce you, or he would do a little bit about the functional data. And then now if you think about the functional data, then eventually what was our goal? Our goal was the prediction, right? Now we know if I have the ordinary type of data, textbook type of data, probably we'll learn some of the basics that how to classify or how to predict. But if you are imagining like functional way, how do you do that? Or if you think about network, how do you do that? And why do I say that repeatedly network? Because Now, one of the idea is that either from the structure, because brain would be network in two ways. One is the structural way, one is the functional way. Like when I'm talking, how the way different neurons are connecting. And there is a physical structural connections. How do I discover this thing? $1 billion questions. And I don't have any answer. But I have data, or you guys can do it. And what I'll talk about, some technique which could be potentially useful, which we have been developing. But you are welcome to join and give some new ideas. Because there will be three things. One is the statistical aspects, because why the statistical aspects? You are extracting, reproducing. There is some uncertainty, inaccuracy. Then there is a data management, computing, and then there is a science itself. Okay, so probably we should take a break, and then we'll be back 11:40. All right.